thanks, Henry, for giving a talk at our seminar. Too bad we couldn't have you in person this time. Who knows, maybe in the future, but yeah, Henry, thanks a lot.
Thanks so much to the organizers for hosting and for the invitation. And yeah, it's too bad we have to do it over Zoom instead of in person, but really appreciate the opportunity to share. So I'll be speaking about a relatively recent topic for me. I've maybe worked on Vietoris-Rips complexes for a decade and Borsuk-Ulam theorems a little bit for about 5 years. But Gromov-Hausdorff distances are a new area of research for me. I mean, they come up in applied topology, right, due to the stability of persistent homology. If you have two metric spaces and they're close in the Gromov-Hausdorff distance, then the persistent homology barcodes are close. And so that's a relationship between Gromov-Hausdorff distances and applied topology. But what we'll actually be studying today is Gromov-Hausdorff distances between spheres of different dimensions. And you can look at their persistence barcodes to get lower bounds on the Gromov-Hausdorff distances, right? Because if the barcodes are far apart, then the Gromov-Hausdorff distances are far apart. But interestingly, those bounds using Rips complexes on Gromov-Hausdorff distances are sort of off by a factor of 2 or so. But what's cool is that you can relate Vietoris-Rips complexes to Gromov-Hausdorff distances in more direct ways, as I'll explain. So this is a joint research project with like roughly 15 or 20 people, all who are either currently or formerly at Colorado State or Ohio State or Carnegie Mellon or Berlin for the most part. And the faculty involved, you know, are myself at Colorado State and Facundo Mémoli at Ohio State and Florian Frick, who maybe applied topologists don't know so well, but he's at Carnegie Mellon and right now at Berlin. And he's worked with Vietoris-Rips. He's worked with me on Vietoris-Rips complexes. But many of our students and Facundo and Florian's cases, their postdocs are sort of helping out on this project. Daniel from Colorado State is here today, and I saw Sunyuk formerly from Ohio State is here today. So it's been a lot of fun working on this polymath-style project. I like collaborative mathematics, and it's not always easy, but I find that's quite productive. Okay, so let me first just introduce Gromov-Hausdorff distances. There's a couple different equivalent definitions. And let me start with the most common definition that we won't actually use most heavily. So it's a notion of distance between metric spaces. So you have two metric spaces and you want to say, what's the distance? First, I'll start with the easier Hausdorff distance. So that Hausdorff distance is when your two metric spaces are embedded in the same place. So on the right here, maybe I have my metric space X, which is a curve, and my metric space Y, which is a set of 20 points, and they're embedded in the same place, the plane. So the Hausdorff distance, one way to define it is the minimum epsilon, such that if you thicken X by epsilon, you contain Y, and if you thicken Y by epsilon, you contain X. So when you thicken X by epsilon, you get this, you know, thickened curve. And that's a big enough epsilon here, right? Because the thickening of X now contains Y. What does it look like when I thicken Y by epsilon? I get this union of balls, I suppose. Okay. And that's also a big enough thickening, epsilon thickening, such that the union of all these balls will contain the curve, right? So that's the Hausdorff distance between two metric spaces embedded in the same place. Just the minimum epsilon, such that if you thicken one by epsilon, you contain the other. The Gromov-Hausdorff distance can be defined even if X and Y are just arbitrary metric spaces. They don't have to be embedded in a common place. Because for the Gromov-Hausdorff distance, you look over all metric spaces Z that admit isometric embeddings of both X and Y, and then you infimize over all isometric embeddings of X and Y into any space Z, and then just look at the Hausdorff distance there. So it's a little, it's very much mathematical definition. It's NP hard to compute. But that gives you the flavor of it. These distances are important both in Riemannian geometry, metric geometry, but also applications to computer graphics. A lot of shape matching problems or shape matching algorithms are inspired by the Gromov-Hausdorff distance. Okay, let me give you a different definition of the Gromov-Hausdorff distance that's equivalent, but it'll be the one that we use. And I'm just gonna define twice the Gromov-Hausdorff distance instead of putting a 1/2 out front. But we infamize over pairs of maps, little g and little h, that go between the two metric spaces in both directions. Okay. So g goes from x to y and h goes back. And we can infamize over any two maps. And crucially, these maps don't need to be continuous. And that'll be one of the main themes of this talk. It's hard for topologists to say things about discontinuous maps, but we'll use Rips complexes to sort of turn discontinuous maps into continuous maps so that we could apply our topological tools. Okay, so you find the best pair of maps, G and H, and then you look at the maximum of three numbers, the distortion of the map G, the distortion of the map H, and the co-distortion. And I need to define these for you. So the distortion of the map G is going from X to Y. So you look at the worst points in X, call them X and X prime. Worst in the sense of how much our distance is distorted when you map from X into Y. So in capital X, the distance between these 2 points is just a little bit. And in capital Y, the distance between their images has gotten larger, right? So the distance between these distances is going to be some positive number once I take the absolute value. And I've distorted the distances, right? And yeah, the distortion is sort of like the worst amount of distortion for any 2 points. Questions about that distortion there? The co-distortion is analogous, but now you look at one point in X and another point in the space capital Y. And now the distances that you compare are X and the image of Y in that space. And you compare that distance to the distance between Y and the image of X, okay? So if the co-distortion were going to be 0, these two distances would be equal. But the discrepancy there, how much you've distorted distances, is this co-distortion. Questions?
So is the right way to think about the distortion is we're kind of measuring how far something is from being in the isometry? Exactly. Right?
Yep.
And then the co-distortion, I'm kind of interested what the motivation of the co-distortion is. What is that measuring?
I mean, it's, of course, it's paying attention to both maps, right? But it's sort of like, I mean, in some sense, we have I can go from points in X to points in Y, but I can also go backwards, right? So it's sort of saying if I measure distances in X, well, they also have sort of evil twin copies in Y. And their distances in X, how do they compare to the distances between their evil twins?
Okay. Yeah.
Interesting in this talk, we're gonna put bounds on the Gromov-Hausdorff distance, lower bounds. And so to lower bound it, we're only gonna have to lower bound one of these terms. So we're actually gonna produce lower bounds by just lower bounding the distortion. We actually won't really see the co-distortion anymore in this talk. So to lower bound the Gromov-Hausdorff distance, we're just gonna lower bound the distortion. because if the distortion is so large, then this maximum is at least that large. So the Gromov-Hausdorff distance is at least that large. Yeah. But yeah, it's sort of like the distortion is the discrepancy from being an isometry, right? An isometric embedding would have distortion 0 because you're not changing the distances at all. Other questions? So let me advertise work by Lim, Mémoli, and Smith. And Lim is Sun-Yuk Lim, who's on the call. So they have this really nice recent paper where they studied Gromov-Hausdorff distances between spheres of different dimensions. They equipped the sphere with the geodesic metric, or the shortest path metric between 2 points on the sphere. And their spheres have diameter pi. So the distance between the North Pole and the South Pole is pi, as it should be. All right, so this is our distance matrix of twice the Gromov-Hausdorff distances. On the diagonal, you should have zeros in the distance matrix, right? So the distance between an n sphere and itself is just 0. It's a symmetric matrix. And for that reason, I'm only gonna talk about the entries in the upper diagonal, above the triangle, above the diagonal, just because you could reflect them to get all the entries down here. So I'll be looking at the distances between Sn and Sk. And in this talk, K will always be bigger than N. And then they prove that all of the non-zero entries are strictly between pi over 2 and pi, okay? So you should think of something close to pi over 2 as a small distance between spheres of different dimensions, and something close to pi is a large distance. Perfect. Yeah, actually, I want to be here. Okay. So they prove a couple distances exactly. They prove that the distance between the circle and the 2 sphere is 2 pi over 3. The distance between the circle and the 3 sphere is 2 pi over 3. And this distance between the 2 sphere and the 3 sphere is R2. Let me describe what R2 is. Okay. So here I have the circle, and I have an inscribed equilateral triangle, and its diameter is 2 pi over 3, right? The distance between 2 points of this triangle is 2 pi over 3. So R1 is just 2 pi over 3. What R2 is you take the 2 sphere, and now you put in an inscribed equilateral or regular tetrahedron, okay? And R2 is the diameter of this tetrahedron, or the vertices of this tetrahedron, okay? And then, R3 would be the same thing, but you do this now in the 3 sphere. You inscribe a regular 4 simplex inside of the 3 sphere. So these distances are sort of tending to pi over 2 as you get larger and larger, because as you look at this, inscribed triangle and then tetrahedron, and then as you increase the dimension, you get the points down at the bottom get closer and closer to the equator. Okay, so you're getting closer and closer to pi over 2. Okay, so these are the only distances that are known exactly. They produce non-trivial lower bounds on all of the other entries of this table, however. So they produce these entries, these lower bounds, which are almost certainly tight, although we don't know that. And they produce a lower bound on a general entry, okay? So for a general entry, the Gromov-Hausdorff distance is at least pi minus this covering number. I'll define this precisely near the bottom of the slide, but the k plus first covering number of Sn is what's the diameter of k plus 1 balls? What's the smallest diameter that's required to cover the n sphere with k+1 balls. Okay. So if you sort of fix n and let k get larger and larger, so what's the Gromov-Hausdorff distance between the 3 sphere and the 4 sphere, 5 sphere, 6 sphere, 7 sphere, 8 sphere, keep going, right? Well, this covering number is getting smaller and smaller because the diameter of balls needed to cover an n sphere gets smaller and smaller as you allow yourself more and more balls, okay? So this bound that they prove shows that in any row, the distance goes to pi as you move along that row, move further and further out. I should say one more thing about their work at the very least, which is, let me give you an indication of how they prove the distance between the circle and the 2 sphere exactly. So remember, you need to produce maps from the circle to the 2 sphere and from the 2 sphere back to the circle that have bounded distortion and co-distortion. Their map from the 2 sphere to the circle looks roughly as follows. So in the northern hemisphere of the 2 sphere, you divide it up into sort of 3 pie-shaped regions. Okay. And each pie-shaped region, all of the points in that pie-shaped region, so maybe this front left pie-shaped region, goes to a point on the equator. And then all of the points in this pie-shaped region, goes to this point on the equator. And then lastly, I guess all the points in this back pie-shaped region goes to this point on the equator. Okay. So it's on the equator, they're the identity. On the North Pole, you divide into pie-shaped regions and you map each pie-shaped region to a single point on the equator. So it's very much a discontinuous map. And then on the Southern Hemisphere, you sort of like do the same thing, but you rotate it by 1/6 of the way before you do that. Okay, so that gives you some flavor of their results. Questions?
Is there some intuitive idea why you would want to set these regions, like map these regions to a constant point? Just because it kind of feels like maybe the distortion would be less if you had sort of like spread it out on the equator a little bit.
Yeah, I mean, Sun-Yuk's the expert here, but my feeling is that I agree with you. Maps that feel natural are more continuous. Yeah. And my conjecture is that there are other maps, that realize this same distortion. But when you try to prove something about the distortion, it actually becomes very easy when it becomes a tool in some sense if large regions collapse to a single point. Because then, sort of in this gray region here, sort of what's the distortion for any 2 points in the gray region, right? Well, the distance between their images is just 0. Mm-hmm. So the distortion for any 2 points in that gray region is just the diameter of that gray region, right? So for proving a distortion, having these sort of like surjective maps onto just a few points is quite easy it's often case-based proofs so far. Yeah. But I think your intuition is the same as mine. It's yet unproven that it'll work. But the hope is that more entries in this table could be filled out by looking at maybe slightly more continuous maps. Yeah.
Cool.
I mean, and Sun-Yuk and his collaborators, they even found nicer maps that computationally had the same distortion, but they couldn't prove it. So, instead of sort of, mapping to 3 points, they looked at things like, mapping to a sinusoidal curve that had 3 humps and stuff like that.
Cool.
Yeah. Sun-Yuk, do you want to say any more?
Yeah, I mean, I agree with the intuition. So there is more sophisticated way to generate the map Z having distortion 2 pi over 3. But as Henry already pointed out, that's the one most tractable map, was easy to deal with. Yeah.
Okay, cool. Thank you.
Mhm.
I was just also going to ask, is this where this covering number comes in, right? Like, are you doing this in the high dimensional case for this bottom statement, right? We're picking, like, doing some subdivision into like covers of some sort and mapping each cover down to a point on the lower dimensional sphere.
I would say intuitively yes, but strictly speaking, no. The covering number is sort of coming in from sort of a volume argument, but it's sort of related to what you're saying. But like, you know, if you want to bound the distortion of these maps between spaces, well, I mean, balls around points in your domain better at least, you know, cover, you know, points in your codomain to sort of bound the distortion. That's the intuition here. I won't. I'll say a little bit more about the covering part in a bit, and then I won't focus on it for the rest of the talk. Okay. So recently, as a larger group with like our 15 people in this polymath project, we provide an improved lower bound. And it's related to something we love, which is the Rips complex, okay? So I'll define the Rips complex for you precisely later, but twice the Gromov-Hausdorff distance between the n sphere and the k sphere is at least as large as the smallest r, such that you need to thicken the n sphere by r, okay? So you need to thicken the lower dimensional sphere by r until it admits an antipodal or odd map from the k sphere. Okay. So how much do you need to thicken this lower dimensional sphere until you admit a nice continuous odd map from the higher dimensional sphere? That will be our CNK. And this provides these new numbers here. So it gives you new lower bounds between the circle and spheres of all dimension. It recovers these lower bounds, but it's only a lower bound. It certainly doesn't prove the equality that was already had here. For an arbitrary entry, it gives a better lower bound than this one, as I'll describe just briefly, because in prior work with my student John Bush and with Florian Frick, we had sort of studied how much do you need to thicken an n sphere until you admit an odd map from a k sphere, and bounded that by covering numbers, but covering numbers of projective space instead of the sphere, right? So, you know, the k covering number is the smallest r such that k balls of diameter r cover your space. Covering the sphere is going to require larger balls than covering the projective space, because the projective space is only half as large. So yeah, this general bound was certainly not tight. This bound is tight in some cases, but in general, it's not going to be tight. It's a good bound, but it's not going to be tight. This bound is tight in all cases that are known so far, but of course we don't know if it's tight always. So, you know, the point of my remaining 25 minutes will be to explain this theorem and its proof, and the mathematical objects in the statement. But more questions here? This is a good spot for them.
I have a quick question here. So in this definition of the CNK, I'm wondering if there's any geometric constraint on this map SK into the Vietoris-Rips, because it feels like just requiring the degree to be odd. This is just a topological property, and I'm wondering why thickenings would change it, like why the sort of geometry of the codomain changes whether or not this map exists.
Yeah, the reason is because the geometry has been moved out to the Rips complex. The definition of the Rips complex is very much related to the geometry of the n sphere, right? So, you know, the vertex set is all points in the n sphere. And then the simplices, a finite subset of the n sphere is a simplex if its diameter is at most r, right? So think of the Rips complexes as like, it's sort of like this parameter space of all subsets of diameter at most r. So this is the geometry here, right?
Okay.
And so it's sort of like, in the Gromov-Hausdorff distance, yeah, it's a geometric thing, right? But what's cool about the Rips complex is it's like, it encodes all subsets of bounded diameter, right? And then once you sort of have that global perspective, we're gonna build a space of all subsets of diameter most r. Then it's sort of like, we've zoomed out enough and looked at all of the geometry at once, that now it's sort of the topology of this parameter space or configuration space that really matters.
Okay, cool.
And this is really cool. This is a perspective that Florian Frick taught me on different projects, because I mean, my motivation for studying Vietoris-Rips complexes is like, in applied topology, if you look at data sets and we build Rips complexes and look at persistent homology. But in the limit, as you sample more and more points of a data set, right? Maybe you're sampling your data set from a manifold, right? So in the limit, you're converging to the persistent homology of the manifold, persistent homology of the Rips complex of the manifold. And nobody knows what the persistent homology of Rips complexes of manifolds are. So we have this data algorithm that's converging to something that we don't understand theoretically. But Florian's perspective is different. It's more like, you know, it's always useful, you know, if you're studying an object, you know, take the algebraic geometry perspective and consider the space of all such objects, you know, and then what's the topology of that space. So it's like, yeah, it's like distortion. If your distortion is at most r, you can like blow things up or perturb things by r and you don't really care, right? So this is sort of like all finite subsets that you're allowed to destroy or blow up or collapse onto a point, and you don't really affect the distortion, right? And once you have all of them together, their topology is what matters. Great question.
Really cool. Yeah, thanks.
Okay. So let me say some things about Borsuk-Ulam theorems. You know, you've probably heard that if you take a two-sphere and map it to the two-dimensional plane, then you have antipodal points that collide. So another way of saying this is that if temperature and pressure are continuous on the surface of the Earth, then there's two antipodal points that have the same temperature and pressure, because that's your map from the surface of the sphere to the 2D plane parameterized by temperature and pressure. You can phrase all these Borsuk-Ulam theorems equivalently in terms of odd maps or antipodal maps or Z mod 2Z maps. So a Z mod 2Z space is just a space that has a free involution. You can map a point to its antipode, and the antipode is supposed to be a different point. So on spheres, you know, our involution is just going to map x to negative x, the antipodal point. An odd map between two Z mod 2Z spaces, it's just an equivariant map. So if you take x and map it to its antipode and then apply f, that's the same thing as first applying f to x and then taking the antipode of the result. Okay, so it's supposed to commute, you know, x going to f of x and then taking the antipode is supposed to be the same thing as if you first took the antipode and then mapped here. And I phrase Borsuk-Ulam as, you know, if you map the two-sphere continuously to the plane, then there's two antipodal points that collide. A different phrasing is that there's no continuous odd map from the two-sphere to the circle. Or, more generally, there's no continuous odd map from the n+1 sphere to the n sphere. So this is basics of equivariant topology, but the Carnegie Mellon and Berlin folks, they study some pretty serious equivariant topology, which we hope to use at some point in our project. Vietoris-Rips simplicial complexes. You have two inputs, a metric space and scale, and you build a simplicial complex where the vertex set is the original metric space. So every point in your metric space is a vertex in the simplicial complex. And you include a set as a simplex if its diameter is at most r. So a picture would be, here I have a metric space with, roughly 10 points, and my scale parameter is 1 inch. So whenever 2 points are within an inch, I connect them by an edge. And then whenever I have 3 edges forming a triangle, I fill in that 2 simplex. And whenever I have all of the edges of a tetrahedron, I fill in that tetrahedron, etc. Questions about Rips complexes?
So,
No,
did you have
no,
a
no.
question? So yeah, I was just wondering, it was super interesting what you said about thinking about the Rips complexes of things like manifolds, and definitely coming from TDA, I hadn't really thought about that deeply before, but like, is it really true that we don't understand much about what happens in the limit, right? Like, I just imagine in the limit, you should have something kind of contractible, right? Like I would assume.
Yeah, so
it's just crazy to me, but.
Yeah, so this is, along with other people, this is my main research area for the past decade, is Rips complexes of manifolds in some sense.
Mm-hmm.
So the circle is understood completely,
mm-hmm.
and the n spheres, only a little bit is known, but it's now becoming, in my opinion, a really important and interesting problem. Mm-hmm. So let me tell you a little bit about Rips complex of the circle. So first of all, the simplicial complex itself is hard to wrap your head around because every point in the circle is a vertex, mm-hmm. right? And so even if your scale is just 1 millimeter, well, you could have a million points that are all within 1 millimeter of each other, right? So you have an infinite dimensional simplicial complex immediately. Right? But Michael Adamaszek and we proved all the homotopy types of Rips complexes of the circle. So for small scales, you always recover the manifold that you start with, okay? You sort of thickened your manifold into this infinite dimensional thing, but you always maintain the homotopy type of the manifold for small scales.
Does the check theorem about having a kind of open cover still hold when it's infinitely many points? So at least in the TDA context, we have a finite point cloud. If we thicken the balls, we have this kind of like nerve theorem, right?
Yes, so yeah, nerve theorems there are fancy nerve theorems that still work for an infinite number of points. Mm-hmm. The nerve theorem would say that the check complex of the manifold is homotopy equivalent to the manifold at small scales, which is true. So this is Hausmann's theorem, that the Rips complex of a manifold recovers the homotopy type of the manifold for small scales. That's a bit harder to prove. So it's not just the nerve theorem. Think of it as a nerve theorem. That's a little more. Once you thicken enough, of course, you get something contractible, right? Like certainly once you reach the diameter of the space, it's definitely contractible. What's surprising though is what happens afterwards, right? In the intermediate ranges, for the circle, in the intermediate ranges, you get the 3 sphere for a range of scales, and then the 5 sphere for shorter range of scales, the 7 sphere, the 9 sphere, the 11 sphere. I love talking about this, and I get plenty of talks on this, and I'd be happy to chat more further. Shoot me an email and we can chat more. But I'll keep it brief here, just so I can relate things back to Gromov-Hausdorff distances. But the rough intuition for why this 3 sphere arises is that at small scales, I get this one solid torus, this thickened circle, okay? Until I reach scale 2 pi over 3, 1/3 of the way around, when this equilateral triangle appears. And that fills it in, except I don't just have one equilateral triangle, I have a circle's worth of equilateral triangles, okay? So to this solid torus in blue that I had originally, think of it as sitting in 3D, I glue on not just one equilateral triangle, which is you should think of as a disk filling it in, but I glue on a circle's worth of equilateral triangles. So each of these is an equilateral triangle. And so I get this, genus 1, Heegard splitting the 3-sphere as 2 solid tori glued together along the hollow torus.
Well, yeah, I honestly didn't expect that. That's crazy.
So yeah, what happens for the circle is cool, and there's more to do here, but in some sense, the homotopy types are fully understood. You get these odd spheres of higher and higher dimensions, which is cool. For higher dimensional spheres, like the 2-sphere, only the first change in homotopy type is sort of known. And that's at this scale when this inscribed n+1 dimensional simplex appears. And yeah, happy to talk more about this new homotopy type that shows up, but maybe I'll have to proceed with the talk for today. So, but these homotopy types tell us the C and K numbers for some choices of n and k, right? So on the circle, how much do I need to thicken until I admit an odd map from the 3-sphere? Well, I need to thicken until the Rips complex has the 3-sphere homotopy type. Okay. And how much do I need to thicken until I admit an odd map from the 5-sphere? I need to thicken until I obtain the odd sphere homotopy type. And how much do I need to thicken the n-sphere until I obtain an odd map from the n+1 or n+2 dimensional sphere? This scale will do. I've bumped up the homotopy type enough that I'll admit an odd map from the n+1 or the n+2 sphere once I get to this scale. I'll bravely plow ahead for now. So Mémoli and Smith, they prove their lower bounds using this nice generalization of Borsuk-Ulam by Dubins and Schwartz, which we're going to generalize. So I just told you there's no continuous odd maps from the n+1 sphere to the n sphere. That's Borsuk-Ulam. Dubins and Schwartz asked this really nice question. In some sense, if you do have an odd map, how discontinuous must it be? Or a related question is how large must its distortion be? So they proved that an odd map from the n+1 sphere to the n sphere must have distortion at least Rn. More generally, what if you look at not just an n+1 sphere to an n sphere, but a k sphere to an n sphere for any k larger than n? And it's got to have distortion at least C and k. So this number that you need to thicken the Rips complex of the n sphere by until you admit an odd map from the k sphere. Basic idea is, okay, let's consider our odd map from the k sphere to the n sphere. We're going to produce a continuous odd map into the Rips complex of the n sphere. Okay, how do we do that? We sample our k sphere really finely and call this sampling x. And we make, x equal to negative x, just so that it produces an odd map. And then we thicken x just a little bit by epsilon, okay? And so these triangles fill in, and tetrahedra fill in. And why do we do that? The reason why we do that is, so now we need to map this k sphere in continuously. Well, first we're just going to map the k sphere into the Rips complex on x. So we use a partition of unity idea. So here's a point on the k sphere. Maybe it lives sort of inside this triangle, So we're going to map it into this triangle in the Rips complex. And you can use the partition of unity idea to do that. And then I didn't get to explain this, but to map from X into the n sphere, well, I already had a map on the entire K sphere into the n sphere. So certainly I have a map from X into the n sphere, because X is just a subset. So the way this map is going to go is, on each vertex X, map it to f of X, and then drag simplices along. Okay, so this edge between vertex X and X prime goes to an edge between f of X and f of X prime. And because f has a certain distortion, this simplicial map will be defined, so long as simplices that are present here get mapped to simplices that are present here. So I need to bump up the scale in order for simplices that are present here to be also present here. But the distortion is how much I need to bump the scale by. Because if X and X prime are within distance epsilon here, then their images are within epsilon plus the distortion of the map. So they're within distortion f plus epsilon here. In any case, I've produced an odd map continuous now from the K sphere to this Rips complex. C and K was defined as the minimum scale such that I admitted such an odd continuous map. Okay, but I've built such an odd continuous map, so the scale must be at least C and K. Let me wrap up and then I'll finish with questions. So we can now prove this theorem that the Gromov-Hausdorff distance is lower bounded by these C and K numbers. Okay, so going back to the definition, what was the Gromov-Hausdorff distance between the n sphere and the K sphere? We looked at the best pair of maps, G and H, and the Gromov-Hausdorff distance was the maximum of three numbers: the distortion of G, distortion of H, and the co-distortion. We're going to forget about these, and we're going to only consider the distortion of the map that goes from the high dimensional sphere to the lower dimensional sphere. Okay. So this maximum is at least as large as the distortion of the map from the high dimensional sphere to the low dimensional sphere. Lim, Mémoli, and Smith proved that you could sort of take any map, forget what it does on the upper hemisphere, and just make it antipodal, and you don't increase the distortion. So therefore, it suffices to consider antipodal maps. And we had just proved this lemma, our generalization Schwartz, was that if you have a odd map from a high dimensional sphere to a low dimensional one, then the distortion was bounded by these C and Ks. All right, so let me end with some open questions. I'll just mention two. One important open question, I think, is what is the homotopy types of Rips complexes of the 2-sphere, the 3-sphere at higher scale parameters before they become contractible? And another open question is, how do you fill out all the rest of the entries of this table? This is mostly what we know now. This is a good lower bound. It's maybe even tight everywhere, maybe is an overly optimistic conjecture, maybe not. But even if it is tight everywhere, we still don't know the entries of the table without understanding the topology of these Rips complexes better. I'll end there. So thanks so much for your time and attention.
Thanks a lot, Henry. Are there any questions in the audience?
So in the Yeah, sorry.
Yeah,
So-
because I couldn't see who like.
okay. Yeah, I don't know if I just dog
No,
someone
go,
there.
go for it, and then.
But yeah, so I mean, there seemed to be something to do with SON or something in the. I can't remember if you made a comment about this.
No, I didn't. I can make.
It just seems kind of psycho.
What's that?
It seems to be crazy.
I like psycho is a good word. Yeah. Yeah. So let me say a little bit about this SON. I'm just gonna destroy this slide here. Okay, so I tried to give you some intuition of where this 3 sphere is coming from, right? It was a circle we had originally, and then sort of joined with the circle's worth of equilateral triangles that got glued in. So you should think of this as S1 join S1, where the first S1 is the circle that we started with, and the second S1 is the circle's worth of equilateral triangles. Okay, but really that S1 is sort of an S1 mod Z mod 3Z, which is still a circle. I mean, if you make a circle 1/3 as long, it's still a circle, right? But the reason why I say S1 mod Z mod 3Z is because, you know, I don't have a full circle's worth of equilateral triangles, because when I rotate an equilateral triangle 1/3 of the way around, I get it back to itself. Okay, so I don't have the full circles of equilateral triangle. The circles of equilateral triangles only 1/3 as long. Okay, but so what I got was my original space joined with the parameter space of critical simplices. The critical simplices were these equilateral triangles, and this is how many equilateral triangles I glued in. Okay, so that's the same thing that's going on here. The new homotopy type is Sn, the space I started with. I was building the Rips complex on Sn, joined with the parameter space of critical simplices I'm gluing on. So let's look at S2. This is going to be S2 join SO3 mod A4. SO3 is just rotations in 3D. So from one equilateral triangle in R3, I could rotate and get in the other. But A4, the alternating group on 4 vertices, that's the rotational symmetries of the simplex, right? So, you know, that's sort of the redundancies. Right? So, yeah, I think joins are really the right perspective here. And the new homotopy types that appear later are likely going to involve joins or partial joins.
That's cool.
I have a kind of a elementary question. Are there some kind of convergence theorem from like a finite sampling of a circle to the continuous setting?
Oh, definitely. I mean, so the stability of persistent homology is one example of this, but I can say more here. So in general, we have there's some notion of distance between barcodes. The bottleneck distance between barcodes. And this is known to be bounded above by the Gromov-Hausdorff distance. Okay, so one answer of your question would be, if 2 metric spaces are close, then their persistent homology barcodes are close, right? So if I take a finite sample from the circle and it's pretty dense, then the persistent homology is going to look something like this, but with some like, you know, some noise. Right? And, you know, if you only take 1,000,000 points on the circle, you won't get up to like this, the odd sphere of dimensions 3,000,001, right? If you take 1,000,000 points on the circle, maybe you only see up to the odd sphere of dimension 5 or 7, who knows? But another comment here, did that first answer your question? Did that make sense?
Yeah. Yeah.
A second answer to your question would be, how did we prove these homotopy types? In a different context, we sort of have a proof that looks a little bit like this, but it's still incomplete, although one of my students, Michael Moy, is greatly generalizing that. But our proof of all of these homotopy types was by understanding Rips complexes of finite subsets of the circle really well. Okay. And one thing that we proved is, let's fix a scale. Okay, so maybe our scale is in this 3-sphere homotopy type region. Okay. We proved that, once your epsilon dense, where epsilon is small enough, then no matter how many more points you sample, the homotopy type is always going to be the 3-sphere. Okay, so we showed once your finite sample is dense enough, then by sampling more points, you don't change the homotopy type anymore. And that's enough to prove the homotopy type of the circle, because the Rips complex of the circle is sort of the union of the Rips complexes of all possible finite subsets. And these finite subsets stabilize in homotopy type, which by using properties of homotopy colimits is enough to prove the homotopy type of the Rips complex of the entire circle. So that was a key step in our proof.
Yeah, I was going to kind of ask a related question, right? Because when you're talking about Rips complexes of manifolds, is it true you have like syntheses of like uncountable dimension as well? Like I don't even.
No, so we still define simplices are always finite. So you say a finite set is a simplex if its diameter is most r. Okay,
so there's infinitely many simplices, but they're all finite dimensional themselves.
Yeah, I usually actually phrase this better than I did here, but we say like a finite set sigma is a simplex if diameter sigma is on the
so that's why we can kind of take colimits of all the finite.
Yeah, so that's why the Rips complex of the circle is the union of the Rips complexes of all its finite subsets. Yeah, and you can look at this diagram of spaces and look at colimits.
So I had a question. I was wondering if I guess in TDA people often talk about Wasserstein distances on top of bottleneck distances, and I'm wondering if there's sort of a Wasserstein version of this where, since we're working with these compact metric spaces, I'm imagining like a Wasserstein version of Gromov-Hausdorff, where you sort of equip everything, I don't know, with like the uniform measure. Think of these as like metric measure spaces and try to prove similar things. And I'm wondering if there might be some relationship between the Gromov-Hausdorff, which seems like the infinity version of it, and I don't know, other choices of P.
Yeah, so I have a lot to say here, and I think Sun-Yuk does too. So Sun-Yuk, I'll let you go next. So you're totally right. There's sort of Wasserstein versions of stability in some contexts, right? I mean, loosely speaking, yeah, what you're saying is related to things I'm very interested in. Fukuda Mémoli and his group, they've defined and studied P Gromov years old by now. I don't have too much to say here. Let me say the following though. So, okay, so yeah, they're sort of like, well, this homotopy type is proved not for the Vietoris-Rips simplicial complex, but for the Vietoris-Rips metric thickening that has a different topology that's defined using Wasserstein distances. So there's Wasserstein stuff staring us in the face everywhere here on all different parts of the project, but I don't know how the different Wasserstein parts relate at all. But like Rips complexes, Wasserstein stuff, optimal transport is now key to the story. Mémoli and others have already thought about Wasserstein versions of Gromov-Hausdorff. Sun-Yuk, I'll let you go. I don't really have anything definite to say.
Yeah, I mean, what I wanted to say is that there's a Gromov-Hausdorff type distances to measure dissimilarity between metric measure spaces.
Okay.
And as far as I know, there's a Sturm's version. I don't remember the precise title of the paper, but it's very famous paper, so you'll be able to find by you typing Sturm in Google Scholar. And another version is that, as Henry pointed out, Facundo, my advisors, P Gromov and distance, it is basically something you expect. We use L-pinum instead of L-infinitum in the definition of the Gromov-Hausdorff distance, and it indeed becomes a metric on the collection of isomorphism classes between metric measure spaces. So yeah, and it has, especially there are many applications, but I'm quite sure there are some application on probabilistic version of persistent homology, and yeah, sorry, I forget that. I don't remember the precise title, but there is Patterson version of the Gromov-Hausdorff distance. So, and there are a lot of research on that, so you'll be able to find that.
Okay, cool. Thank you very much for your answer.
Are there any other questions? I think not. Okay. Well, thank you again, Henry, for your talk. Too bad you couldn't make it. I'm really sorry about that. But,
yeah, look forward to to meeting you all in person hopefully soon.
Yeah, you were so close, so much closer than we were at the same time.
Yeah.